In this video, we're talking about cylinders and quadric surfaces. A quadric surface is a second-degree equation in three variables, meaning that there are going to be an x, a y, and a z variable present, and at least one of them would be raised to a square power. So we have seen a quadric surface before. A sphere is a special case, and just as a reminder, this would be the equation of a sphere centered at the origin with a radius of r, and the general equation for a sphere would be x minus h, y minus k, and z minus, let's say, l, and that would have a center at the ordered triple h, k, l, and a radius of r. So now let's generalize this idea a little bit more. We see that the general equation of a quadric surface offers many more combinations of x, y, and z, but we do have to have that possibility of at least one of the x, y, or z values being squared. There are several ways to go about graphing a quadric surface, but before we get into that, let's make a couple more definitions. First of all, a plane curve. Let's consider the three-dimensional coordinate system and a plane that is somewhere inside here. So just an arbitrary plane drawn somewhere in the three-dimensional coordinate system. A plane curve is a curve that exists entirely within the plane. So we could have, say, an ellipse or something that is in this plane. A plane curve could also be entirely contained in a plane that is slanted or coming in at any direction, really. So we could have a plane curve that looks like this. As long as the entire curve is contained within the plane, it's considered to be a plane curve. A cylinder is going to have a more general definition than what we traditionally think of as a cylinder. A cylinder is a surface that's containing all lines parallel to a given line and passing through a given plane curve. So let's go back to the drawing of the original plane curve that we had a moment ago, where we have a plane and an ellipse that is entirely contained within that plane, so we have an elliptical plane curve. The cylinder is going to consist of all lines that are going to be parallel to a given line. So let's say our given line would be a line passing through this plane curve, and all of the lines that are going to be parallel to that will also be considered to be part of the cylinder. It's kind of hard to draw all of the lines, but essentially those lines are going to create that outer surface that is this cylinder, right? So all of the lines parallel to those given lines are going to be on the outside here, passing through this plane curve that was the ellipse, okay? So cylinders can actually take on any shape. We do have a special case of a cylinder that we traditionally think of as a cylinder. A right circular cylinder would be a cylinder that passes through a circle. But the plane curve can be any shape. It could be a triangle, and we would still be able to have a triangular cylinder. So let's take a look at our first example here. And what we'll notice right off the bat is that we are missing the variable y. If we're missing the y variable, then what we're going to do is graph a 2D plane curve that exists entirely in the plane of the variables that are present. So the 2D plane curve is going to be graphed in the xz plane. And so what we can do initially is start off with a two-dimensional drawing where we look at the x as the horizontal axis and the z-axis being the vertical axis, and we'll consider this to be the xz plane. And once we get an idea for what it looks like in the xz plane, then we'll take it over to the three-dimensional coordinate system and see if we can expand on our graph. So first of all, in the xz plane, we can kind of rewrite this as being negative x squared plus 4 so that it looks more familiar. This is actually going to be a parabola that has been shifted up 4 units and is been vertically flipped. So we'll look here and go up 2, 3, 4 units, and we're going to have a parabola that's opening down, and we can also tell that that parabola is going to be crossing the x-axis, so we have x-intercepts when x is equal to positive 2 and when x is equal to negative 2. We also, of course, have the ordered pair when x is 0, z is 4. And we can say then that this is going to look like a parabola opening down in the xz plane. So let's come over to our three-dimensional coordinate system and essentially graph that plane curve that z is equal to negative x squared plus 4 in the xz plane, in the plane of the two variables that are contained in the equation. So as we saw a moment ago, we have a z intercept at the x value being equal to 0. If I'm in the xz plane, the y value is also 0, and then the z value would be 4. We also have the ordered triples that when x is equal to positive 2, of course, the y value is going to be 0 if we're in the xz plane. So for all these ordered triples that we're creating in three-dimensional space, we're going to have y is equal to 0, and then z is equal to 0. And then as well, we have negative 2 for x, y is 0, z is 0. And then we're just going to sketch that opening down parabola. Again, this is a plane curve because it exists entirely in the xz plane. However, this original graph was a three-dimensional graph, one to be graphed in R3. We start by graphing it in the xz plane, and then when we take it over into 3 dimensions, we're going to say that the missing y variable means that we are going to take this plane curve and extend in the direction of the variable that is missing. So we're going to extend in the direction of our y variable. Essentially, this is going to become a cylinder. We're going to extend each of these ordered triples in the direction of y. So we have a line that is passing through the plane curve. And as a matter of fact, we're going to want all the lines that pass through this plane curve. And the graph is going to end up kind of taking this plane curve and sliding it left and sliding it right until what we end up with is something that has the shape of kind of like a mailbox. So we're extending all of these ordered triples in the direction of y, and we end up with this surface. This is a quadric surface, and it is going to look much better when we take this over into GeoGebra to try to come up with an image. So let's do that now so that we can kind of clean up the way that this graph is looking. We are in geogebra.com, and we've selected the calculator option, 3D calculator. This is getting us into three-dimensional space, and so we'll just type in our equation. So we input our z is equal to negative x squared and then plus 4, and we can see that we do have this parabolic cylinder. If we were to zoom in or to arrange it to where we're looking just down on the xz plane, we see that two-dimensional graph that we had, right? Our graph has a z-intercept at 0, 4, an x-intercept at negative 2 and positive 2, and then it essentially is going to fly out in the direction of x. So we're including all of the lines that pass through that plane curve and are parallel to one another, and that's giving me this cylinder. So our cylinder that we graphed was correct.